The sun is dying. Not today, not tomorrow, but its death is already written into the fabric of reality. Every single second, deep in the core, 600 million tons of hydrogen vanish forever. They fuse into helium through nuclear fusion, releasing the light and heat that makes all life on Earth possible. This process has been running without pause for 4.6 billion years, consuming fuel at a rate beyond human comprehension. The fuel supply is vast, staggering even by cosmic standards, but it is not infinite. In roughly 5 billion years, the hydrogen at the sun's core will be completely exhausted. The fusion reactions that have powered our star since before the Earth existed will sputter and die. When that moment arrives, the sun will transform into something unrecognizable, something monstrous. It will swell into a red giant, its outer layers expanding far beyond the orbit of Mars, perhaps even reaching Jupiter. The transformation will be gradual by human standards, taking millions of years, but inevitable nonetheless. Mercury will be consumed first, its rocky surface vaporized in the expanding stellar atmosphere. Venus will follow, its thick clouds offering no protection against the sun's final embrace. Earth's fate remains uncertain. Some models suggest our planet might survive, pushed into a more distant orbit by the sun's mass loss during its red giant phase. But even if Earth escapes being swallowed whole, survival means nothing. The planet will be reduced to a charred, airless cinder, its surface temperature hot enough to melt lead. Every ocean will have long since boiled away, every mountain reduced to molten rock. Nothing recognizable will remain. Long before that final expansion, long before the sun becomes a red giant, life on Earth will have already ended. In approximately 1 billion years, perhaps slightly less, the sun's gradual brightening will push our planet past a critical threshold. The increased solar radiation will trigger a runaway greenhouse effect, a cascade from which there is no return. The oceans, which have existed for nearly 4 billion years, will begin to evaporate. Water vapor, a potent greenhouse gas, will trap more heat, accelerating the process further. Within a few 100 million years, every drop of liquid water on Earth's surface will be gone, lost to space or locked in minerals deep underground. The atmosphere will become a toxic steam bath, temperatures soaring past anything life can endure. Every organism that depends on liquid water, which is to say every organism we know of, will perish. The Earth will become a second Venus, a hell world beneath crushing skies. Right now, in this moment, you are living under the light of a middle-aged star in its prime. The Sun is what astronomers classify as a G-type main sequence star, a designation that indicates it occupies the stable middle phase of stellar life. It has been burning steadily, fusing hydrogen into helium, since before the Earth even solidified from the swirling disk of gas and dust that surrounded the infant sun. Every organism that has ever existed on this planet, every single breath ever taken by any living thing, every heartbeat ever felt, has depended entirely on the energy released by this one star. The warmth you feel on your skin comes from nuclear fusion 93 million miles away. The food you eat exists because plants captured that same light and converted it into chemical energy. The oxygen you breathe was produced by organisms powered by sunlight. The weather patterns, the ocean currents, the very habitability of this world all trace back to hydrogen nuclei colliding with impossible violence in a place you will never see. You exist because of fusion. You exist because a star is dying slowly enough that life had time to evolve. The sun is not eternal, despite how it appears in our daily lives. It is a temporary phenomenon, a brief flash of warmth in the cold darkness of space. It is dying, and so, in a very real sense, are we. The light touching your face right now is older than human civilization. The photons warming your skin began their journey long before you were born, quite possibly before your species even existed on Earth. A photon created in the sun's core does not simply travel outward in a straight line and arrive at Earth 8 minutes later. The journey through the sun itself takes between 10,000 and 170,000 years, depending on the path each individual photon happens to take. The core is so unimaginably dense that light cannot move freely through it. A cubic centimeter of core material would weigh more than 150 grams here on Earth, packed so tightly that photons can travel only a fraction of a millimeter before slamming into an atom. Photons collide constantly with the surrounding matter, bouncing in random directions like a ball trapped in an infinite, three-dimensional pinball machine with no exit. Each collision redirects the photon, forcing it onto a new trajectory that bears no relation to its original direction. It might move upward for a moment, then sideways, then back down toward the core again. Progress toward the surface is statistical, not intentional. This region of constant scattering is called the radiative zone, and it extends outward from the core to about 70% of the sun's radius. Within this zone, energy moves through an endless dance of absorption and re-emission, photons being destroyed and recreated trillions upon trillions of times. Only after tens or even hundreds of thousands of years does a photon finally, through pure random chance, reach the boundary of the convective zone. Here, the physics changes. The plasma becomes less dense, and massive convection currents take over. Rising columns of superheated gas, each one larger than our entire planet, lift the photon toward the surface. Meanwhile, cooler plasma sinks back down in enormous cells, creating a churning, boiling motion. The photon rides these convection currents upward, no longer bouncing randomly, but carried along with the flow, until it finally breaks free from the sun's surface and escapes into space. The subsequent 8-minute trip from the sun's surface to Earth, covering 93 million miles at the speed of light, is the easiest and fastest part of the entire voyage. By the time sunlight reaches you, it has already traveled through deep time in a very literal sense. The warmth you feel on your skin, the brightness you see in the sky, both are ancient beyond normal comprehension. Some of the photons striking your retina at this very moment were created in the core when Neanderthals still roamed the forests of Europe, hunting woolly mammoths beneath Ice Age skies. Others were born during the rise and fall of the Roman Empire, emerging from the core while legions marched across continents. Still others began their journey during the construction of the Egyptian pyramids, or during the last Ice Age, or during periods so remote that humans had not yet learned to make fire. Every sunrise is an archive of millennia made visible, a museum of deep time displayed across the sky. The core, where all of this begins, where every photon starts its ancient journey, exists in conditions that defy ordinary understanding. The temperature there reaches 15 million degrees Celsius, a number so large it loses meaning. At this temperature, matter cannot exist in any form familiar to us. There are no solid objects, no liquids, not even conventional gases. Atoms are completely stripped of their electrons, torn apart by the sheer violence of the heat. What remains is a plasma, a sea of bare atomic nuclei racing through a fog of free electrons, all moving at tremendous speeds. The pressure at the core is 300 billion times the atmospheric pressure at sea level on Earth. Under these extreme conditions, hydrogen nuclei, which under normal circumstances repel each other fiercely due to their positive electrical charges, are forced into such close proximity that they overcome that repulsion. They collide with such violence that the nuclear force takes over, binding them together. They fuse, forming helium nuclei and releasing tremendous amounts of energy in the process. Energy that will eventually, after thousands upon thousands of years, emerge as the light of day. This is the engine that powers the sun. This is the furnace that has burned without interruption for 4.6 billion years. And the light it creates takes longer to escape the star than entire human civilizations last from rise to fall. The process destroying the sun is also the process that keeps you alive. Every single second, without pause, the core consumes 600 million tons of hydrogen. To put that in perspective, imagine every car, building, ship, and aircraft humanity has ever constructed. Then multiply that entire mass by thousands. That much hydrogen vanishes every second, converted into something else entirely. This is nuclear fusion, the fundamental power source of stars. Hydrogen nuclei, which are simply individual protons, collide in the extreme heat and pressure of the core with tremendous violence. Under normal circumstances, this fusion should be completely impossible. Protons carry positive electrical charges, and like charges repel each other with tremendous force. The electromagnetic force pushing them apart grows stronger the closer two protons get to each other. At ordinary temperatures and pressures, they can never overcome this electromagnetic repulsion. But the sun's core is not ordinary by any measure. At 15 million degrees Celsius and 300 billion atmospheres of pressure, protons move at incredible speeds, racing at thousands of kilometers per second. And they are squeezed so close together that quantum mechanics begins to dominate. Through a phenomenon called quantum tunneling, protons can effectively bypass the electromagnetic barrier that should keep them apart. They don't have enough energy to overcome the repulsion in the classical sense, but quantum mechanics allows them to appear on the other side anyway, as if passing through a solid wall. When this happens, when two protons get close enough for the strong nuclear force to take over, they fuse together in a reaction that releases energy. Through a series of subsequent reactions, 4 hydrogen nuclei eventually combine to form one helium nucleus. But here's the critical detail that powers everything. The helium nucleus produced weighs slightly less than the 4 hydrogen nuclei that created it. A tiny amount of mass, less than 1% of the original mass, has vanished. That missing mass hasn't disappeared into nothing. It has been converted into energy, according to Einstein's famous equation E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is roughly 300 million meters per second, an enormous number. When you square that number, it becomes almost incomprehensibly large. This means even a tiny amount of mass converts into a staggering amount of energy. If you could convert a single kilogram of matter into pure energy, it would release as much power as burning millions of tons of coal. The fusion of hydrogen into helium releases this energy in the form of high-energy photons, gamma rays, that begin the long journey outward through the sun's layers. This is the engine that has powered the sun for 4.6 billion years, without stopping, without slowing, without rest. 4.6 billion years ago, When the sun first ignited fusion in its core, the world was unrecognizable. Dinosaurs were still billions of years in the future. The Earth was a molten ball of rock, bombarded constantly by asteroids. The Moon had just formed from the debris of a catastrophic collision. Life did not yet exist anywhere in the solar system. The fusion reactions in the Sun's core have been running continuously since that ancient moment, every single second of every single day, consuming hydrogen, producing helium, releasing light and heat into space. The fuel supply is vast, truly vast by any human measure. The Sun contains enough hydrogen to continue this process for billions of years more. But vast does not mean infinite. The hydrogen is finite. The countdown is underway, and it cannot be stopped. The power output of the Sun defies human comprehension. Every single second, the Sun radiates 3.8 times 10 to the 26th watts of energy into space. That number is so large, it becomes meaningless without context. So consider this. Humanity's entire energy consumption throughout all of recorded history, every fire ever lit, every engine ever run, every light bulb ever switched on, every power plant that has ever operated, all of it combined, represents less energy than the Sun outputs in a single second. 1 second of the Sun's power output exceeds thousands of years of human civilization's total energy use. And the Sun has been doing this every second for 4.6 billion years. The sheer physical scale of the Sun is equally difficult to grasp. If you could somehow hollow out the Sun and fill it with Earths, you could fit 1.3 million of our planet inside. Not hundreds, not thousands. 1.3 million Earths. The Sun's diameter is 109 times that of Earth. If you placed Earth and the Sun side by side, you would need to line up 109 Earths in a row to match the distance across the Sun's face. In terms of mass, the disparity becomes even more extreme. The Sun weighs 333,000 times more than Earth. If you wanted to balance the Sun using Earths as counterweights, you would need roughly 1/3 of a million Earths. In fact, the Sun accounts for 99.86% of all the mass in the entire solar system. Jupiter, Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury, all the moons, all the asteroids, all the comets, all the dust and gas scattered through interplanetary space, all of it combined represents barely more than 1/10 of 1% of the solar system's total mass. Everything else is essentially a rounding error compared to the Sun. The Sun is the solar system, and everything else, including us, is just debris orbiting that vast central concentration of matter. And that mass creates gravity powerful enough to hold 8 planets in their orbits across billions of miles. Mercury orbits at roughly 36 million miles from the Sun, still firmly locked in the Sun's gravitational grip. Neptune orbits at 2.8 billion miles away, 30 times farther from the Sun than Earth. Even at that immense distance, even separated by billions of miles of empty space, the Sun's gravity is still strong enough to keep Neptune bound. Neptune takes 165 Earth years to complete a single orbit, moving at over 12,000 miles per hour through space, and yet it never escapes. The Sun's gravitational influence reaches even farther, holding the Kuiper Belt and the distant Oort cloud, extending perhaps 2 light-years from the Sun. At those distances, the Sun would appear as just another bright star in the black sky, but its gravity still dominates, still holds those distant objects in orbit, still defines the boundary of the solar system. This is the scale of the object that gives us life. A ball of plasma so massive it warps space-time around it, creating the gravity well in which we live. So hot, it tears atoms into their constituent parts, stripping electrons away. So powerful, it has shaped everything in our corner of the cosmos, from the orbits of planets to the evolution of life itself. And yet, by cosmic standards, the Sun is completely unremarkable. It is a medium-sized star, neither particularly large nor particularly small, neither exceptionally hot nor unusually cool. It is, in almost every measurable way, average. And that ordinariness is perhaps the most extraordinary thing about it. Because it means the universe is filled with stars like this, billions upon billions of them scattered across space, each one a furnace of unimaginable power, each one anchoring its own system of worlds. There are particles escaping the Sun's core right now that pass through you as if you don't exist. They are called neutrinos, and they are the universe's ultimate ghosts. Unlike photons, which bounce endlessly through the Sun's interior for thousands or hundreds of thousands of years, neutrinos escape the core instantly. The moment they are created during fusion reactions, they simply leave, passing through the entire mass of the Sun as if it were empty space. The Sun is incredibly dense, with matter packed so tightly that photons barely move a millimeter without colliding. But to neutrinos, density means nothing. They experience almost no electromagnetic force, no strong nuclear force, affected only by the weak nuclear force and gravity, both extraordinarily feeble at the particle level. Right now, trillions upon trillions of neutrinos from the Sun are passing through your body every single second. They stream through the walls of your room, through the ground beneath your feet, through the entire planet, and out into space without even slowing down. Most will travel through the universe forever, without ever interacting with anything. They could pass through a barrier of solid lead, stretching for light years, and almost none would be stopped. A light year of lead would barely slow them. They are, for all practical purposes, invisible and intangible, particles that occupy the same universe as matter, but barely acknowledge its existence. This makes neutrinos incredibly difficult to detect, but also incredibly valuable. They are the only particles that escape the Sun's core immediately, carrying information about what's happening there right now, at this very moment. Every photon we see began its journey tens or hundreds of thousands of years ago in the core. The light tells us about the Sun's past, about fusion reactions that happened when ice ages came and went. But neutrinos tell us about the present, about fusion reactions happening right now, this second. They are messengers arriving just minutes after they're created, bringing news from a place we can never directly see. Detecting these ghost particles requires extraordinary measures. Neutrino detectors are built deep underground, buried beneath mountains or in mine shafts, shielded from cosmic rays and other particles. Some sit beneath thousands of feet of rock, others at the bottom of lakes, using water as both shielding and detection medium. These detectors contain vast tanks filled with heavy water or pure water, sometimes thousands of tons of liquid sitting in enormous chambers. The apparatus waits for the incredibly rare moment when a neutrino actually interacts with an atom. When this happens, the collision produces a flash of light that sensitive instruments can detect. But these events are vanishingly rare, perhaps a few per day, even in the largest detectors. For decades, beginning in the 1960s, physicists faced a troubling mystery called the solar neutrino problem. Their detectors were finding only about 1/3 of the neutrinos that theory predicted. 2/3 were missing. Either our understanding of how the sun works was fundamentally wrong, or something very strange was happening to the neutrinos during their journey. The answer turned out to be even more bizarre than anyone imagined. Neutrinos were changing type, oscillating between different varieties, transforming as they traveled through space. There are 3 types of neutrinos, and the sun produces only electron neutrinos through fusion. But by the time these neutrinos reach Earth, many have transformed into muon neutrinos, or tau neutrinos. Early detectors could only detect electron neutrinos, so they missed 2/3 entirely. Solving this mystery required accepting that neutrinos have mass, a tiny amount, but enough to allow them to oscillate between types. The discovery won the Nobel Prize in Physics in 2015, resolving a problem that had puzzled scientists for more than 30 years. And it confirmed that our understanding of the sun's core is correct, that fusion really does work the way theory predicts. The neutrino deficit wasn't a problem with the sun. It was a problem with our understanding of neutrinos themselves. The ghosts had spoken, and we finally learned how to listen. The sun is not a uniform ball of plasma, but a precisely structured object with distinct layers, each governed by different physics. At the very center lies the core, occupying only the innermost 25% of the sun's radius. This tiny central region, just a quarter of the sun's size, generates 100% of the star's energy. Everything else, the vast bulk of the sun, exists only to contain and transport that energy outward. Surrounding the core is the radiative zone, extending from 25% of the radius out to roughly 70%. This zone is so dense that energy cannot flow freely. Instead, it moves through countless absorptions and re-emissions, photons being swallowed by atoms and then released again, over and over, in random directions. The radiative zone is where photons begin their long, slow journey, where time stretches out and light becomes trapped in the maze of matter. The plasma here is relatively stable, not churning or mixing, just incredibly dense and hot. At about 70% of the radius from the center, conditions change dramatically. The temperature has dropped enough, and the density has decreased enough that radiation alone can no longer transport all the energy trying to escape. Convection takes over. The outer 30% of the sun's interior is the convective zone, where massive currents of plasma rise and sink in enormous cells. Hot plasma, heated from below, becomes less dense and rises toward the surface like a hot air balloon. When it reaches the surface, it radiates its heat into space, cools, becomes denser, and sinks back down again. These convection cells are larger than Earth, massive rivers of plasma flowing upward and downward, creating the churning, boiling motion that defines the sun's outer layers. This is the same process that makes water boil in a pot, just scaled up to stellar proportions with temperatures in the millions of degrees. Each zone has its own distinct physics, its own rules. The core is the realm of nuclear fusion, where quantum mechanics allows the impossible. The radiative zone is dominated by photon diffusion, a random walk that takes millennia. The convective zone is ruled by fluid dynamics, by the motion of hot and cold currents, by turbulence on a cosmic scale. And between the radiative zone and the convective zone lies a boundary called the tachocline. The tachocline is a thin, sheer layer, only about 2 to 4% of the sun's radius in thickness, where rotation changes from one pattern to another. The radiative zone below rotates almost like a solid body, all at roughly the same rate. But the convective zone above rotates differentially, with the equator spinning faster than the poles. The tachocline is where these two different rotation patterns meet and interact, creating shear forces and turbulence. This boundary layer is believed to be critical for generating the Sun's magnetic field, though the exact mechanisms are still not fully understood. What is certain is that the tachocline plays a major role in solar activity, in sunspots and flares, and all the violent phenomena that affect Earth. As you move outward through these layers, from core to surface, the temperature drops dramatically. At the very center, 15 million degrees Celsius. At the boundary between the radiative and convective zones, about 2 million degrees. By the time you reach the visible surface, the photosphere, the temperature has fallen to just 5,500 degrees Celsius. Still hot enough to vaporize any known material, but a mere fraction of the core's fury. This temperature gradient drives everything: the outward flow of energy, the convection currents, the light we see. The Sun is an engine of layers, each one essential, each one contributing to the star's stability and longevity. Remove any layer, change any boundary, and the entire structure would collapse or explode. It is a system in balance, held together by gravity and driven by fusion, a machine that has run without failure for 4.6 billion years. The Sun has no surface in the way Earth does. There is no solid ground, no rocky boundary, no point where gas ends and something else begins. What we call the Sun's surface, the photosphere, is simply the layer from which light can finally escape into space after its long journey from the core. It is the point where the Sun becomes transparent enough that photons can break free. The photosphere is a layer of gas, plasma still hot enough to glow brilliantly white, but cool enough by stellar standards that it appears as a defined edge when viewed from Earth. Everything below this layer is opaque, hidden from view. This visible layer is remarkably thin, only about 400 kilometers deep from bottom to top. 400 kilometers sounds substantial until you compare it to the Sun's total radius of nearly 700,000 kilometers. The photosphere represents less than 0.1% of the Sun's radius. If the Sun were an apple, the photosphere would be thinner than the apple's skin. Yet this thin layer is where virtually all the visible light we see originates. The temperature here has dropped from the millions of degrees in the core to 5,500 degrees Celsius. At this temperature, atoms can hold on to some of their electrons, creating the conditions for emitting yellow-white light. If you could observe the photosphere closely, you would see that it is not smooth or uniform. The entire visible surface is covered in a constantly shifting pattern called granulation. These granules are the tops of convection cells, vast columns of hot plasma rising from deep within the convective zone below. Each granule represents where hot plasma reaches the surface, spreads outward, releases its heat, and then cools and sinks back down around the edges. The granules are enormous, each one roughly the size of Texas or larger, spanning 1,000 to 1,500 kilometers across. From Earth, even through powerful telescopes, they appear as a fine, rice-grain texture covering the Sun's face. But despite their immense size, granules are surprisingly short-lived. Each one lasts only 8 to 20 minutes before the convection cell driving it changes or dissipates. The hot plasma cools as it radiates energy, the bright center fades, and new granules form elsewhere as fresh plasma rises. The Sun's surface is constantly churning, constantly renewing itself, a boiling sea of plasma that never rests. High-resolution images show this motion clearly, granules appearing and disappearing, bright centers dimming while new spots emerge. It is a mesmerizing dance of light and heat, playing out on a scale that dwarfs anything on Earth. There is another phenomenon visible on the photosphere that reveals the sun's structure. When you look at an image of the sun, the center appears noticeably brighter than the edges. This effect is called limb darkening. When you look at the center of the sun's disk, you are looking straight down through the photosphere, penetrating deep into hotter, brighter layers below. But when you look toward the edge, the limb, you are looking at an angle. Your line of sight passes through cooler upper layers without penetrating as deeply into the hot regions. These cooler layers emit less light, so the limb appears darker, even though the plasma there is still thousands of degrees hot. This simple effect reveals that the photosphere is stratified, with temperature and density decreasing as you move upward. Limb darkening tells us the photosphere is just the beginning, the first visible layer of a complex atmosphere extending far beyond what our eyes perceive. What lies above is stranger still. Above the photosphere lies a realm that remains mostly invisible, a layered atmosphere that only reveals itself under special circumstances or through specialized instruments. The first layer beyond the photosphere is the chromosphere, a thin region of gas that glows with a distinctive reddish color. The chromosphere is only about 2,000 kilometers thick, barely visible under normal conditions because the brilliant photosphere below it drowns out its faint light. But during a total solar eclipse, when the moon blocks the photosphere, the chromosphere becomes briefly visible as a thin red ring around the sun's edge. That red color comes from hydrogen atoms emitting light at a specific wavelength as they are energized by the intense radiation from below. The chromosphere is hotter than the photosphere beneath it, reaching temperatures of about 20,000 degrees Celsius. This is already strange, the temperature increasing as you move away from the sun's core, but it is just the beginning of a much deeper mystery. The chromosphere is not a calm, quiet layer. It is filled with dynamic structures called spicules, jets of plasma that shoot upward from the surface like geysers. These spicules are enormous, each one extending 10,000 kilometers or more into space, tall enough to dwarf Earth. They rise at speeds of 50 to 150 kilometers per second, moving faster than any hurricane or tornado on Earth. And yet, despite their violence, each spicule is short-lived, lasting only 5 to 10 minutes before falling back or dissipating. At any given moment, thousands of spicules are erupting across the sun's surface, creating a constantly shifting forest of plasma jets. They carry mass and energy upward from the chromosphere into the layers above, though their exact role in heating the outer atmosphere remains under investigation. Beyond the chromosphere lies the corona, the sun's outer atmosphere, and here the mystery deepens into something truly baffling. The corona extends millions of kilometers into space, far beyond the visible disk of the sun. It is so diffuse, so tenuous, that under normal circumstances it is completely invisible, its faint light overwhelmed by the brilliance of the photosphere. But during a total solar eclipse, when the moon blocks the sun's bright face, the corona appears as a magnificent halo of white light streaming outward in all directions. Photographs of eclipses show delicate streamers and loops of glowing gas, structures shaped by the sun's magnetic field, extending vast distances into space. The corona's beauty is matched only by its strangeness. The temperature of the corona is 1 to 2 million degrees Celsius, sometimes even hotter during periods of high activity. This is hundreds of times hotter than the photosphere below it. This makes no sense according to basic thermodynamics. Heat should flow from hot regions to cool regions, and yet somehow the corona, far from the fusion furnace of the core, is vastly hotter than the layers closer to the heat source. This is called the coronal heating problem, and it remains one of the greatest unsolved mysteries in solar physics. Scientists have been struggling to understand it for more than 70 years. The best current theory involves magnetic waves, disturbances in the sun's complex magnetic field that propagate upward through the atmosphere. These waves carry energy from the convective zone below, and when they break or dissipate in the thin plasma of the corona, they release that energy as heat. Think of it like ocean waves breaking on a shore, converting the kinetic energy of moving water into sound and spray. But in the corona, the waves are magnetic, and the energy converts into heat at temperatures that can melt any known substance. Other mechanisms may also contribute, including magnetic reconnection events, where twisted magnetic field lines snap and reconfigure, releasing bursts of energy. But despite decades of observations from ground-based telescopes and space-based observatories, despite sophisticated computer simulations, the exact mechanisms remain unclear. The corona is a place where the normal rules seem to break down, where distance from the heat source somehow leads to higher temperatures, where the sun's atmosphere becomes stranger and more violent the farther you go from its surface. It is a reminder that even our closest star, the object we depend on for life, still holds profound mysteries that challenge our understanding of physics. There are dark marks that appear on the sun's surface, regions that look like blemishes or scars against the brilliant photosphere. They are called sunspots, and they represent places where the sun's hidden magnetic forces break through to the visible surface. Sunspots are cooler than their surroundings, with temperatures around 4,000 degrees Celsius compared to the photosphere's 5,500 degrees. This temperature difference of 1,500 degrees might not sound dramatic, but it is enough to make them appear noticeably darker. In reality, sunspots are not dark at all. If you could somehow isolate a sunspot and view it against the blackness of space, it would glow brightly, radiating more light than an electric arc welder. But against the intense brilliance of the surrounding photosphere, they appear as dark spots, shadows on the face of the sun. This is purely an optical contrast effect, a trick of relative brightness. They look dark because everything around them is so much brighter. Sunspots form in regions where the sun's magnetic field becomes concentrated and twisted. The sun's interior is in constant motion, with plasma flowing and rotating at different rates depending on latitude. This motion generates and amplifies magnetic fields through a process called the dynamo effect. Sometimes these magnetic field lines become tangled and concentrated, creating regions of intense magnetic activity. When these field lines break through the photosphere, they suppress the normal convection of hot plasma from below. The magnetic field acts like a dam, preventing the hottest plasma from rising to the surface in that location. Without the constant supply of fresh, hot material, the region cools slightly, becoming a sunspot. The magnetic field strength in a sunspot can be 2,500 times stronger than Earth's magnetic field at its surface. This is an enormous concentration of magnetic energy, powerful enough to affect the behavior of plasma across thousands of kilometers. Some sunspots grow to enormous sizes, larger than the entire planet Earth. The largest sunspots can span 50,000 kilometers or more across, big enough that multiple Earths could fit inside a single spot. These giant spots are visible even through basic solar filters or safe projection methods, appearing as obvious dark patches on the sun's face. Sunspots rarely appear alone. They typically form in pairs, and this pairing reveals something important about their magnetic nature. Each pair represents a loop of magnetic field line that has emerged from beneath the photosphere. One spot marks where the field line exits the surface, the other marks where it re-enters. One spot will have a north magnetic polarity, the other a south polarity, just like the opposite poles of a bar magnet. The magnetic field lines connecting the paired spots arc high above the photosphere, creating invisible bridges of magnetic force that trap and guide plasma in the layers above. These loops can sometimes be seen in special telescope images as bright structures in the corona. Sunspots can persist for varying lengths of time. Small spots might last only a few days before fading. Larger, more stable sunspot groups can endure for weeks or even months, rotating with the sun's surface as the star spins. As they rotate, they move across the visible face of the sun from our perspective on Earth, appearing on the eastern limb, traveling across the disk, and disappearing around the western edge. If they last long enough, they will reappear roughly 27 days later as the sun completes one rotation. Humans have observed sunspots for centuries, though their true nature remained mysterious for a long time. Galileo Galilei was among the first to study them systematically, using a telescope in the early 1600s. His observations of sunspots were controversial because they challenged the prevailing belief that the sun was a perfect, unchanging celestial sphere. The presence of spots, blemishes that appeared and disappeared, suggested the sun was dynamic and imperfect, an idea that contradicted the philosophical assumptions of the time. Galileo's careful tracking of sunspots also proved that the sun rotates, as he watched the spots move across the solar disk in consistent patterns. These dark marks on the sun, once considered imperfections, became windows into understanding the star's nature, revealing its magnetic complexity and its constant state of change. The sun has a heartbeat, a rhythm that pulses through its activity over the course of roughly 11 years. This is the solar cycle, a periodic rise and fall in the number of sunspots visible on the sun's surface. During solar minimum, the sun appears almost spotless, with days or even weeks passing without a single sunspot appearing. The star seems calm, quiet, with minimal magnetic activity breaking through to the photosphere. But this calm does not last. Slowly, over months and years, sunspot activity begins to increase. More spots appear, and they grow larger and more numerous. Solar activity builds gradually toward solar maximum, the peak of the cycle, when the sun's face can be covered with dozens of sunspot groups at once. During this phase, the sun is magnetically active, energetic, prone to powerful eruptions and storms. Then, just as gradually, the activity declines again. Sunspots become less frequent, smaller, until the sun returns to minimum and the cycle begins anew. This entire process, from one minimum to the next, takes an average of 11 years. But there is more structure to this cycle than just the number of spots. The latitude where sunspots appear follows a distinctive pattern over the course of each cycle. At the start of a new cycle, the first sunspots appear at relatively high latitudes, around 30 to 35 degrees north and south of the sun's equator. As the cycle progresses toward maximum, new sunspots form at progressively lower latitudes, migrating toward the equator. By the end of a cycle, during the declining phase, sunspots are appearing close to the equator, around 5 to 10 degrees latitude. Meanwhile, the first spots of the next cycle have already begun appearing at high latitudes again. When you plot the latitude of sunspots over time, the pattern creates a distinctive shape called the butterfly diagram. Each cycle creates two wings, one in the northern hemisphere and one in the southern, with spots starting at high latitudes and drifting toward the equator over 11 years. The diagram looks like a series of butterfly wings opening and closing over and over, a visual representation of the sun's magnetic rhythm. But the most dramatic change during the solar cycle happens to the Sun's magnetic poles. At the beginning of each 11-year cycle, the Sun's north and south magnetic poles have specific polarities, just like Earth's magnetic field has a north and south pole. But as the cycle progresses, something extraordinary happens. The magnetic field weakens, becomes disordered, and then reverses completely. By the time the sunspot cycle reaches its maximum, the Sun's magnetic north pole has become a south pole, and the magnetic south pole has become a north pole. The entire global magnetic field has flipped. This means the true magnetic cycle of the Sun is actually 22 years, not 11, because it takes 2 sunspot cycles for the magnetic field to flip and then flip back to its original configuration. Scientists are currently tracking the ongoing solar cycle, known as Solar Cycle 25, which began in December 2019. The predicted maximum for this cycle is expected around 2025, though the exact timing is difficult to predict precisely. One of the frustrating aspects of the solar cycle is its variability. While 11 years is the average, individual cycles can be as short as 9 years or as long as 14 years. The length is not constant or predictable with perfect accuracy. And the strength of each cycle varies dramatically as well. Some solar maxima produce intense magnetic activity, with large, numerous sunspots and frequent powerful eruptions. Other maxima are relatively weak, with fewer spots and less energetic events. Solar Cycle 25 is predicted to be a moderate cycle, neither particularly strong nor particularly weak. But predictions about solar cycle strength have proven unreliable in the past, so observers will have to wait and watch to see how active the Sun truly becomes. The 11-year cycle is the Sun's most obvious rhythm, a heartbeat we can see and measure from Earth. It affects space weather, satellite operations, power grids, and communication systems. It is a reminder that the Sun is not a static, unchanging light in the sky, but a dynamic, breathing star, whose moods shift in patterns that we are still learning to predict and understand. There was a time when the Sun's heartbeat nearly stopped. For 70 years, from 1645 to 1715, sunspots almost completely disappeared from the Sun's surface. This period is called the Maunder Minimum, named after the astronomer Edward Maunder, who documented it in the late 1800s by studying historical records. During these 7 decades, observers recorded almost no sunspots, maybe a handful scattered across years that should have seen hundreds or thousands. The normal 11-year cycle seemed to have shut down entirely. The Sun entered a state of minimal magnetic activity, a prolonged solar minimum unlike anything seen in the centuries since. And during this same 70-year period, Earth's climate changed dramatically. Europe, North America, and other regions experienced what is now called the Little Ice Age, a time of significantly colder temperatures than the centuries before or after. The connection between these two events, the quiet sun and the cold climate, has been debated by scientists for decades. Winters in Europe became brutally harsh during the Maunder Minimum. The Thames River in London, which rarely freezes today, froze solid regularly during this period. Historical records describe frost fairs held on the thick ice, with merchants setting up booths, people roasting meat over fires, and even skating and sledding on the frozen river. Paintings from the era show these frozen rivers, cities blanketed in snow, and people bundled against cold that seemed harsher than anyone could remember from earlier times. The canals of the Netherlands froze solid enough to support carriages and crowds. Glaciers in the Alps advanced, consuming villages and farmland that had been inhabited for generations. Growing seasons shortened across northern Europe. Crop failures became more common, leading to famines and hardship. The Baltic Sea froze in ways it had not done before, disrupting trade routes. Iceland became surrounded by sea ice for much of the year, isolating the island and making life even more difficult for its inhabitants. Was the quiet sun responsible for this cold period? The timing is suggestive, but the cause and effect relationship remains debated and uncertain. The sun's energy output varies by only about 0.1% over the solar cycle, a tiny change that seems insufficient to trigger such dramatic climate effects. Yet the correlation between the Maunder minimum and the Little Ice Age is hard to ignore. Some scientists suggest that the sun's magnetic activity, rather than its total energy output, might influence Earth's climate through complex mechanisms involving cosmic rays, cloud formation, or atmospheric chemistry. Others argue that volcanic activity, ocean circulation changes, or other factors might explain most or all of the cooling. The debate continues, with no clear consensus. What is certain is that the Maunder minimum shows the sun is capable of dramatic changes in behavior. The solar cycle is not an unchanging clockwork mechanism, but something that can shift, weaken, or even shut down for extended periods. The sun entered a state it had not been in before, at least not in recorded history, and eventually emerged from it. By 1715, sunspots began reappearing with more regularity. The 11-year cycle resumed, and solar activity returned to something closer to modern levels. The climate gradually warmed again, glaciers retreated, and the Little Ice Age ended. The Maunder minimum serves as a reminder that the sun, despite its apparent stability over human lifetimes, can change in ways that affect Earth. It reveals a star capable of long-term variability beyond the predictable 11-year rhythm we observe today. And it raises an uncomfortable question. Could it happen again? Could the sun fall silent for decades once more? And if it did, what would it mean for Earth's climate in an era already grappling with human-caused warming? The sun's past behavior suggests that drastic changes, while rare, are possible. On the morning of September 1st, 1859, two amateur astronomers in England were independently observing the sun through telescopes. What they witnessed was unprecedented. They saw a brilliant white flash appear on the sun's surface, a sudden brightening that lasted about 5 minutes before fading. This was the first time anyone had ever observed a solar flare in visible light. They had just witnessed the beginning of the most powerful solar storm ever recorded in human history. 17 hours later, a massive cloud of magnetized plasma slammed into Earth's magnetic field with tremendous force. The impact triggered the most intense geomagnetic storm ever documented, now known as the Carrington event, named after Richard Carrington, one of the observers who saw the initial flare. The effects were immediate and spectacular. Auroras, normally confined to polar regions, appeared as far south as the Caribbean, Hawaii, and Colombia. People in Cuba and Jamaica saw the northern sky glowing with curtains of red, green, and white light. In the Rocky Mountains, gold miners woke in the middle of the night thinking it was dawn because the auroras were so bright. Some people could read newspapers by aurora light alone. The sky glowed with such intensity that birds began chirping, confused by what seemed like an early sunrise. But the auroras were just the visible manifestation of something far more disruptive. The telegraph network was thrown into chaos. Telegraph systems across Europe and North America experienced massive power surges as the geomagnetic storm induced electrical currents in the wires. Operators received electric shocks from their equipment. Some telegraph stations caught fire as the surges overloaded the systems. In some cases, operators disconnected the batteries and found they could still send messages using only the electricity induced by the storm itself. Compass needles spun wildly, rendered useless by the disturbance in Earth's magnetic field. Ships at sea lost their ability to navigate as their compasses gave false readings or simply rotated aimlessly. The Carrington event was a direct assault on human technology by the sun. And it happened in 1859, when infrastructure was far less dependent on electricity than today. If an event of similar magnitude struck Earth now, the consequences would be catastrophic. Modern estimates suggest that a Carrington-level storm could cause more than $1 trillion in damage to global infrastructure. Power grids would be the first casualty. The geomagnetic storm would induce massive electrical currents in long-distance power transmission lines, potentially destroying transformers across entire continents. Large transformers take months or even years to manufacture and replace. If hundreds or thousands were damaged simultaneously, power could be out for months across vast areas. Satellites would be bombarded with high-energy particles, damaging electronics and potentially causing permanent failures. GPS systems could become unreliable or non-functional, disrupting navigation for aircraft, ships, and ground vehicles. Communication systems would face severe disruptions. Radio communications could become impossible in some frequency ranges. The internet could suffer widespread outages. The good news is that we now have warning systems. Modern satellites monitor the sun constantly, detecting solar flares and coronal mass ejections as they happen. We can have anywhere from 15 minutes to several days of warning, depending on the speed of the ejected material. Power companies can take protective measures, putting systems into safe modes and disconnecting vulnerable equipment. Satellites can be placed into protective orientations, and astronauts can take shelter in shielded areas. Airlines can reroute flights away from polar regions where radiation exposure is highest. But warnings only help if action is taken, and the scale of a Carrington-level event might overwhelm even the best preparations. The sun has the power to reach across 93 million miles and disrupt human civilization. The Carrington event happened less than 200 years ago, and the sun is still capable of producing such storms today. The sun's magnetic field is not a simple, stable structure like Earth's relatively orderly north-south dipole. It is a tangled, twisted, constantly evolving web of magnetic force generated by the sun's internal motions. This magnetic field is created through a process called the dynamo effect, one of the most important and complex mechanisms operating within the sun. The dynamo begins with the sun's rotation and the churning convection currents in its outer layers. But here is where things become complicated. The sun does not rotate like a solid object. Different parts of the sun spin at different rates, a phenomenon called differential rotation. The equator completes one rotation in about 25 days, while regions near the poles take roughly 35 days to make the same journey. This difference in rotation speed has profound consequences for the sun's magnetic field. Imagine magnetic field lines threading through the sun from pole to pole, like invisible wires running through the interior. As the equator rotates faster than the poles, these field lines get stretched and twisted, wound around the sun like rubber bands being wrapped around a ball. Over time, months and years, the field lines become increasingly tangled and concentrated. The magnetic field strength grows in certain regions as the lines pile up on top of each other. Eventually, these twisted, concentrated field lines become buoyant and rise toward the surface, breaking through the photosphere. When they emerge, they create sunspots, active regions, and all the violent magnetic phenomena we observe on the sun's surface. This is how differential rotation drives the solar dynamo, turning the sun's rotation into magnetic energy. The convective motions in the outer layers also play a crucial role, stirring and amplifying the magnetic field. Hot plasma rising and cool plasma sinking drag magnetic field lines with them, stretching and twisting them further. The combination of differential rotation and convection creates a self-sustaining cycle. The sun's motion generates magnetic fields, and those magnetic fields, once created, affect the motion of the plasma, which in turn affects the magnetic field. This feedback loop has been operating for billions of years, creating the 11-year solar cycle and all the magnetic activity we observe. But the twisted field lines do more than just create sunspots. When magnetic field lines become too twisted, too stressed, they can suddenly snap and reconfigure in a process called magnetic reconnection. This is one of the most energetic and explosive processes in nature. Magnetic reconnection occurs when oppositely directed magnetic field lines come close together and break, then reconnect in a new configuration. During this process, the magnetic energy stored in the twisted field lines is suddenly converted into kinetic energy, heat, and radiation. The energy release is instantaneous and immense. A single reconnection event can release as much energy as billions of nuclear bombs detonating at once, heating plasma to tens of millions of degrees and accelerating particles to nearly the speed of light. Magnetic reconnection is the engine behind solar flares, coronal mass ejections, and many other violent solar phenomena. It is the mechanism that allows the sun to suddenly unleash vast amounts of stored magnetic energy into space. The twisted magnetic field created by the dynamo is not just a passive feature of the sun. It is the source of almost all the sun's variability and violence. Every solar flare begins with magnetic reconnection. Every coronal mass ejection is driven by the sudden reconfiguration of twisted magnetic field lines. The aurora, visible on Earth, the geomagnetic storms that threaten our technology, the radiation that endangers astronauts, all of it traces back to the sun's magnetic dynamo. The dynamo is the sun's engine of chaos, a mechanism that takes the orderly rotation of the star and transforms it into complex, unpredictable magnetic structures. And despite decades of study, the exact details of how the dynamo operates remain partially mysterious. We understand the basic principles, but predicting exactly when and where the magnetic field will erupt remains one of the great challenges in solar physics. The sun's magnetic field is invisible to our eyes, but it shapes everything we see happening on the sun's surface and in its atmosphere. To understand solar activity, scientists needed a way to map these invisible forces. That mapping tool is called a magnetogram, an image that shows the strength and direction of magnetic fields across the sun's visible surface. Magnetograms are created using specialized instruments that measure the Zeeman effect, a subtle splitting of spectral lines caused by magnetic fields. In a magnetogram, regions of strong magnetic field appear bright, while areas of weak field appear dark. Regions where field lines point toward us appear in one color, typically white, while regions where field lines point away appear in another, typically black. These images reveal the sun's hidden magnetic skeleton, the underlying structure that drives all solar activity. Magnetograms show magnetic field lines emerging from the sun's interior, rising up through the photosphere as bright and dark patches. These emerging field lines often form loops, arching high above the surface before diving back down into the photosphere at a different location. One end of the loop has a north magnetic polarity, the other end has a south polarity, creating paired magnetic structures. These loops are not static. Some remain stable for days or weeks, gracefully arching through the corona, confining hot plasma in their magnetic embrace. Others are unstable, twisted, and prone to sudden eruptions. The difference between a stable loop and an explosive one can be subtle, a matter of how much twist the field line has accumulated, or how much stress has built up in the magnetic structure. By tracking magnetograms over time, scientists can watch the evolution of the magnetic field, seeing how new field lines emerge, how existing structures change and twist, and how regions of magnetic activity grow or fade. This evolution provides clues about what the sun might do in the hours or days ahead. Certain magnetic configurations are known to be more dangerous than others. Regions where oppositely directed field lines come close together are prime candidates for magnetic reconnection, meaning they could produce flares or eruptions. Areas where the magnetic field is rapidly changing or becoming more twisted suggest that energy is building up, waiting to be released. Scientists use these patterns to predict solar activity, issuing alerts when dangerous configurations appear. But despite these tools, despite decades of observations and increasingly sophisticated computer models, predicting exactly when a solar flare will occur remains frustratingly difficult. We can identify regions that are likely to flare, but pinpointing the exact moment of eruption, hours or even minutes in advance, is still beyond our capability. The magnetic field is simply too complex, too dynamic, with too many interacting structures and processes happening simultaneously. A region that looks stable can suddenly erupt without warning, while a region that appears on the verge of exploding can remain quiet for days. The sun's magnetic field operates on scales from thousands of kilometers down to meters or smaller, far beyond our ability to observe directly. Small-scale magnetic structures, invisible in our instruments, can trigger large-scale eruptions. It is like trying to predict exactly when an avalanche will start by observing a snow-covered mountain from a distance. You can see the dangerous conditions. You can identify slopes that are likely to avalanche. But the exact trigger, the precise moment and location, remains hidden. This is the challenge facing solar physicists today. We can see the invisible magnetic forces through magnetograms. We can track their evolution. We understand the basic physics of how they produce eruptions. But the sun's magnetic field remains, in many ways, unpredictable. It is a reminder that even with our best instruments and deepest understanding, the sun still holds secrets, still surprises us, still defies our attempts to predict its behavior with perfect accuracy. The invisible forces are visible now, mapped and measured, but they remain stubbornly beyond our complete control or prediction. Solar flares are the sun's most sudden and violent outbursts, explosions of light and energy that can outshine the entire sun in certain wavelengths. They are the result of magnetic reconnection happening at incredible speeds. When twisted magnetic field lines snap and reconfigure, the stored energy releases all at once. The plasma caught in those magnetic fields is suddenly heated to tens of millions of degrees, sometimes over 100 million degrees. Electrons and protons are accelerated to nearly the speed of light in a matter of seconds. The flare emits a burst of radiation across the entire electromagnetic spectrum, from low-energy radio waves all the way up to high-energy X-rays and gamma rays. Solar flares are classified by their X-ray brightness, with categories labeled A, B, C, M, and X, each one 10 times more powerful than the previous. X-class flares are the strongest, the most dangerous, capable of affecting Earth even across 93 million miles of space. Within the X-class, the scale continues upward with numbers. An X2 flare is twice as powerful as an X1. An X10 flare is 10 times as powerful. The largest flare ever recorded was an X28 in 2003, though it likely peaked even higher but saturated the instruments measuring it. The energy released in a major solar flare is almost incomprehensible. A single X-class flare can release energy equivalent to billions of nuclear bombs detonating simultaneously. To put this in human terms, the energy from one large flare could power human civilization at current consumption rates for hundreds of thousands of years. And the sun releases this energy in minutes, sometimes in seconds. The flare begins with a sudden brightening, visible in specialized telescopes that observe specific wavelengths like X-rays or extreme ultraviolet light. In these images, the flare appears as an intensely bright flash, far brighter than the surrounding corona. The brightness peaks rapidly, climbing to maximum intensity in just a few minutes, sometimes faster. Then it begins to fade, declining over minutes to hours depending on the flare's strength. Some flares are visible even in normal white light, like the one Richard Carrington observed in 1859. These white light flares are exceptionally rare and powerful, representing the most extreme events the sun can produce. The radiation from a solar flare travels at the speed of light, which means it reaches Earth in just over 8 minutes. There is no warning, no time to prepare once the flare erupts. By the time we detect the flare with our instruments, the radiation has already crossed half the distance to Earth. By the time we could issue a warning, it would already be here. But flares do more than just release radiation. They often accelerate particles to extreme velocities, creating beams of high-energy protons and electrons that stream outward from the sun. These solar energetic particles move at significant fractions of the speed of light, arriving at Earth within minutes to hours after the flare. And in many cases, particularly with the most powerful flares, magnetic reconnection also launches a coronal mass ejection, a massive cloud of magnetized plasma that follows behind the initial radiation blast. The flare is the opening act, the sudden explosion of light. The coronal mass ejection is the follow-up punch, slower but carrying far more mass and energy, capable of triggering severe geomagnetic storms when it eventually reaches Earth days later. Together, a major flare and an associated CME represent one of the most powerful and dangerous phenomena in the solar system. Solar flares remind us that the sun, despite appearing stable and constant in our sky, is capable of sudden, violent outbursts that can reach across interplanetary space and affect our world. The sun does not need to physically touch Earth to influence it. Light and magnetism alone are enough. The moment a solar flare erupts, the race begins. High-energy X-rays and extreme ultraviolet radiation stream outward from the sun at the speed of light, crossing 93 million miles in just over 8 minutes. There is no shielding from this radiation, no way to block it once the flare has occurred. By the time satellites detect the flare and scientists realize what has happened, the radiation has already arrived at Earth. The X-rays and extreme UV radiation do not reach the ground, fortunately. Earth's atmosphere absorbs them high above our heads in a layer called the ionosphere. The ionosphere is a region of the upper atmosphere where solar radiation normally ionizes molecules, creating a layer of charged particles that reflects radio waves. This layer is what makes long-distance radio communication possible, allowing signals to bounce around Earth's curve. But when a solar flare hits, the sudden surge of X-rays and UV radiation supercharges the ionosphere. The ionization intensifies dramatically on the sunlit side of Earth, the side facing the sun when the flare erupts. This enhanced ionization disrupts radio wave propagation, particularly at high frequencies. Radio signals that normally bounce off the ionosphere are instead absorbed by the over-ionized layer. The result is a radio blackout, a sudden loss of high-frequency radio communications across the entire sunlit hemisphere of Earth. These blackouts can last from minutes to hours, depending on the strength of the flare. For most people, this is invisible and goes unnoticed, but for certain industries and operations, it is a serious problem. Aviation relies heavily on high-frequency radio for communication, especially over oceans and polar regions where there is no ground-based infrastructure. Pilots flying transoceanic or transpolar routes suddenly lose their primary communication method when a solar flare strikes. Airlines monitor space weather forecasts and sometimes reroute flights away from polar regions when strong solar activity is expected, because radiation exposure is also higher at these latitudes during solar storms. But a sudden, unexpected X-class flare can catch flights in mid-journey with no warning. Military and emergency services that rely on high-frequency radio also experience disruptions. Ships at sea, remote research stations, disaster response teams all can find themselves suddenly cut off from reliable communication. GPS signals can also be affected, though through a different mechanism. The ionospheric disturbance changes how GPS signals propagate through the atmosphere, introducing errors in position calculations. Navigation systems may show incorrect locations, or the accuracy may degrade from meters to tens of meters or worse. For precision applications like aircraft landing systems or surveying equipment, this degradation can be significant. The warning time for solar flare impacts is essentially zero. The radiation travels at light speed, so it arrives at the same time we see the flare occur. Satellite instruments detect the X-ray spike and send alerts within seconds, but by then, the Earth is already being bathed in the radiation. The disruption to the ionosphere begins immediately and peaks within minutes. The impacts typically last from tens of minutes to a few hours for most flares. As the enhanced radiation fades, the ionosphere gradually returns to normal, and radio communications are restored. But during those minutes or hours, the effects are global across the entire day side of Earth. A flare powerful enough to cause a complete radio blackout will affect an entire hemisphere, disrupting communications for billions of people simultaneously. Unlike coronal mass ejections, which take days to arrive and can be tracked and predicted, solar flare radiation is instantaneous. We cannot prevent it, cannot shield against it, cannot warn people to take cover before it arrives. We can only watch it happen, measure its effects, and wait for the ionosphere to recover. It is an assault by light, invisible to our eyes, but very real in its consequences. And if the flare is accompanied by a coronal mass ejection, as the most powerful flares often are, then the radiation blackout is just the first wave of a much larger storm that will arrive 1 to 3 days later. The sun's violence comes in layers, fast and slow, light and matter, each with its own timeline and its own dangers. While solar flares are explosions of light and radiation, coronal mass ejections are something more physical, more massive, more like a punch than a flash. They are enormous clouds of magnetized plasma hurled into space by the sun's violent magnetic activity. A coronal mass ejection, or CME, occurs when the sun's twisted magnetic field lines become so stressed that they suddenly break free from the surface, launching billions of tons of plasma outward into the solar system. These eruptions often accompany powerful solar flares, but not always. Sometimes a CME launches without any visible flare. Other times a flare occurs without producing a CME. But the largest, most dangerous solar events typically involve both: a flare releasing the energy, and a CME carrying that energy outward as physical matter. The scale of a coronal mass ejection is difficult to grasp. A single CME can contain 1 billion tons of plasma, sometimes much more. That is roughly the mass of a small mountain or a large iceberg. But instead of rock or ice, it is super-hot ionized gas traveling through space at tremendous speed. The plasma cloud expands as it moves outward, growing wider and wider. Some CMEs become larger than the Sun itself, spanning more than 1,000,000 kilometers across by the time they reach Earth's orbit. They are not solid objects, but diffuse clouds, with density far lower than Earth's atmosphere, yet still containing enough material to significantly affect any planet they encounter. The speed of a CME varies dramatically depending on the energy of the eruption that launched it. Slow CMEs might travel at 400 kilometers per second, still faster than anything on Earth, but relatively sedate by cosmic standards. Fast CMEs can exceed 3,000 kilometers per second, roughly 1% of the speed of light. The fastest CMEs ever recorded have reached speeds approaching 4,000 kilometers per second, driven by the most powerful magnetic reconnection events. At these velocities, a CME can cross the 93 million miles from the Sun to Earth in as little as 15 to 18 hours. More typical transit times are 1 to 3 days, depending on the CME's speed and the conditions in the solar wind it travels through. Unlike solar flare radiation, which arrives in 8 minutes, CMEs give us warning time. We can track them as they move through space using satellites positioned between the Sun and Earth. These satellites image the approaching plasma cloud and measure its speed, direction, and magnetic properties. Scientists can predict, with reasonable accuracy, when a CME will arrive at Earth, and how strong the resulting geomagnetic storm might be. But here is the critical detail that makes some CMEs far more dangerous than others. Each CME carries its own magnetic field, frozen into the plasma as it was launched from the Sun. This embedded magnetic field has a direction, an orientation in space. When the CME reaches Earth, its magnetic field will interact with Earth's magnetic field. If the two fields are aligned in the same direction, the interaction is relatively mild. But if the CME's magnetic field points southward, opposite to Earth's northward pointing field, the interaction becomes severe. The oppositely directed fields can merge through magnetic reconnection, allowing the CME's energy to pour directly into Earth's magnetosphere. Unfortunately, we cannot know the magnetic field orientation of an approaching CME until it is very close, often just 30 to 60 minutes before impact. This is one reason why precise prediction of CME effects remains challenging. And most CMEs miss Earth entirely. The Sun erupts CMEs in all directions, launching them across a wide range of angles. Earth is a small target in a vast solar system. Even a CME that appears to be heading our way in telescope images might pass above or below Earth's orbit, or to the side, never making contact. Only a fraction of all CMEs are Earth-directed, and even among those, the magnetic field orientation determines whether the impact will be minor or major. But when all the factors align, when a fast, massive CME with a southward magnetic field strikes Earth directly, the results can be spectacular and dangerous. The Sun launches these plasma bullets regularly, sometimes multiple times per week during solar maximum. Most pass harmlessly through space, their violence expended on empty vacuum. But every so often, one finds its mark. When a coronal mass ejection reaches Earth, it slams into the invisible magnetic bubble that surrounds our planet. Earth's magnetosphere, the region of space dominated by our planet's magnetic field, acts as the first line of defense. The magnetosphere normally extends about 60,000 kilometers toward the Sun and trails out behind Earth for hundreds of thousands of kilometers. But when a CME hits, everything changes. The impact compresses the magnetosphere dramatically, pushing it inward from 60,000 kilometers to perhaps 30,000 or less. The entire magnetic field structure shudders under the pressure of the incoming plasma. What happens next depends critically on the orientation of the CME's magnetic field. If the CME's field points northward, parallel to Earth's field, the two magnetic structures push against each other. The interaction is strong, but much of the CME's energy is deflected around the magnetosphere. But if the CME's magnetic field points southward, the situation becomes far more dangerous. Southward pointing magnetic fields can merge with Earth's northward field through magnetic reconnection. When this happens, the CME's magnetic field essentially plugs directly into Earth's magnetic field. A pathway opens, allowing energy and particles from the CME to pour into the magnetosphere. Charged particles, electrons and protons, are funneled along Earth's magnetic field lines toward the polar regions. When these high-energy particles slam into the upper atmosphere near the poles, they collide with oxygen and nitrogen molecules, causing them to emit light. This creates the aurora, the northern and southern lights. During a major geomagnetic storm, the auroras become spectacular, bright enough to read by, and they expand far beyond their normal polar regions. During the Carrington event, auroras were visible in the Caribbean. During the Quebec blackout storm of March 1989, auroras were seen as far south as Texas. But the auroras are just the visible symptom of what is happening to Earth's magnetic field. The geomagnetic storm creates rapidly changing magnetic fields around the planet. These changing fields induce electrical currents in any long conductor, including power transmission lines and pipelines. In power grids, the induced currents are called geomagnetically induced currents, or GICs. These currents flow into transformers, the critical components that regulate voltage in the power grid. Transformers are designed to handle alternating current at specific frequencies, not the quasi-direct current produced by geomagnetic storms. The GICs can cause transformers to saturate, overheating them and potentially causing permanent damage. If enough transformers fail across a region, the entire grid can collapse. This is exactly what happened in Quebec on March 13, 1989. A powerful CME struck Earth, triggering a severe geomagnetic storm. Within 90 seconds of the storm's peak, the entire Quebec power grid collapsed. 6 million people were left without power for 9 hours, some for longer. The storm damaged transformers across North America. And this was far from the worst-case scenario. The 1989 storm was strong, but not in the same class as the Carrington event. A Carrington-level CME impact today would likely cause widespread, long-lasting power failures across multiple continents. The vulnerability comes from our dependence on interconnected systems. Modern power grids are vast, spanning thousands of miles, with long transmission lines that act like giant antennas for induced currents. The more connected the grid, the more vulnerable it becomes. And replacement transformers for the largest units can take months or years to manufacture and install. When a CME strikes, we face a test of our technological resilience. The sun's power extends far beyond warmth and light. It can reach across interplanetary space and touch the delicate systems we have built. Systems that are strong in many ways, but fragile in others. Our technological civilization has become exquisitely vulnerable to the sun's outbursts in ways that would have been unimaginable a century ago. We have surrounded ourselves with systems that depend on stable conditions in space and in Earth's magnetic environment. Satellites are among the most exposed and vulnerable pieces of our infrastructure. Thousands of satellites orbit Earth, providing communications, navigation, weather monitoring, and military capabilities. These satellites operate in a harsh environment, but when a solar storm strikes, that environment becomes actively hostile. High-energy particles from solar flares and coronal mass ejections bombard satellites directly. There is no atmosphere to absorb or deflect this radiation at orbital altitudes. The particles penetrate satellite hulls and strike sensitive electronics, causing malfunctions or permanent damage. A single high-energy particle hitting the wrong component can flip a bit in computer memory or trigger errors. In extreme cases, the radiation can destroy semiconductor junctions, rendering entire systems inoperable. Solar panels degrade over time from exposure to radiation. During intense solar storms, this degradation accelerates as high-energy particles damage the crystalline structure of solar cells. GPS satellites are particularly critical, and their disruption affects far more than navigation apps. The GPS constellation provides precise timing signals used by financial networks, power grids, and telecommunications systems. When solar storms disturb the ionosphere, GPS signals passing through that region become corrupted. Position calculations can be off by tens of meters, and receivers may lose lock entirely. Aircraft relying on GPS for precision approaches must switch to backup systems. Survey equipment and precision agriculture systems lose accuracy. On the ground, long-distance power transmission lines act as enormous antennas, picking up energy from changing magnetic fields during geomagnetic storms. These geomagnetically induced currents flow through the grid. The currents are quasi-direct currents that can saturate transformer cores. Transformers operate inefficiently under these conditions, heating up and sometimes overheating. The largest transformers are custom-built and cost millions of dollars. Each one takes months or years to manufacture and replace. If hundreds fail simultaneously during a major storm, power could be out for months across entire regions. Even pipelines buried underground are not immune. Changing magnetic fields induce currents in long metal pipes, accelerating electrochemical corrosion at weak points. Pipeline operators must account for space weather in maintenance schedules. And airline crews flying at cruising altitude receive increased radiation during solar storms, particularly on polar routes where Earth's magnetic field provides less shielding. For crew members who fly frequently, cumulative radiation exposure can approach regulated levels. During severe solar storms, airlines reroute flights away from polar regions, adding flight time and fuel costs, but protecting crew and passengers. The FAA and similar agencies monitor space weather and issue advisories when radiation levels become concerning. Our civilization has created a web of interconnected systems, each useful and powerful, but collectively forming a structure with unexpected vulnerabilities. The Sun, 93 million miles away, can reach out and touch all of them. For astronauts working beyond Earth's protective atmosphere, a solar storm is not an inconvenience or a threat to infrastructure. It is a direct, potentially deadly hazard. In space, there is no atmosphere to absorb the high-energy particles and radiation that the Sun hurls outward during flares and coronal mass ejections. What would be absorbed hundreds of kilometers above Earth's surface becomes a direct threat to human tissue and electronics in spacecraft. When a solar flare erupts, high-energy protons and other particles stream outward at significant fractions of the speed of light. These solar energetic particles arrive at Earth within minutes to hours, depending on their energy. Spacecraft hulls provide some shielding, but they are thin by necessity. Every kilogram of mass costs enormous amounts of money to launch into orbit, so spacecraft cannot be built like bunkers. The radiation doses astronauts receive during a major solar particle event can be significant. In the worst cases, they could receive doses large enough to cause acute radiation sickness, damaging cells, suppressing immune function, and increasing long-term cancer risk. The International Space Station has shielded areas where astronauts can take shelter during solar storms. These are typically the most heavily shielded modules, or areas surrounded by supplies, water tanks, and equipment that provide additional mass to absorb radiation. When ground-based space weather monitoring detects a major solar flare or an incoming particle storm, Mission Control alerts the astronauts. They move to the shielded areas and wait out the storm, which can last hours or days. During this time, they cannot perform spacewalks or work in less protected areas of the station. The station itself may experience temporary malfunctions or computer glitches as radiation strikes sensitive electronics. But the International Space Station orbits at an altitude where Earth's magnetic field still provides some protection. The field deflects many particles away from the station, and astronauts can quickly reach shelter when needed. For missions beyond low Earth orbit, the situation becomes far more dangerous. The Moon has no magnetic field and no atmosphere. Astronauts on the lunar surface during a major solar particle event would need to shelter immediately, either in heavily shielded habitats or behind terrain features that could block the incoming radiation. A solar flare happening during a moonwalk could force astronauts to abandon their activities and return to safety within minutes. Mars missions face even greater challenges. The journey to Mars takes 6 to 9 months, a long time to be exposed to space radiation with no possibility of returning to Earth's protection. During this transit, a major solar particle event could expose the crew to dangerous radiation levels. Mars spacecraft will need dedicated radiation shelters, heavily shielded areas where the crew can retreat during storms. These shelters add mass, complexity, and cost to the mission, but they are not optional. Without them, a single large solar storm during the months-long journey could deliver doses high enough to compromise the crew's health, or even be lethal. And unlike astronauts on the ISS, who receive warnings from Earth-based monitoring systems, crews traveling to Mars will be much farther from the Sun's Earth-facing side. They will need their own onboard monitoring systems and more advanced warning to take shelter in time. The Sun's radiation is not the only challenge, but it is one of the most unpredictable and potentially deadly. We can shield against the steady background of cosmic radiation with enough mass and planning, but the sudden, intense bursts from solar flares and particle events are harder to defend against. They require advance warning, rapid response, and adequate shielding, all while operating in an environment where resources are limited and mistakes can be fatal. For now, astronauts on the ISS have relatively good protection and plenty of warning time. But as humanity ventures farther from Earth, beyond the protective cocoon of our planet's magnetic field, the Sun's violence becomes a more serious concern. Space exploration is dangerous in many ways, but solar radiation is one hazard that comes directly from the star we depend on for life.